Hi, good morning. My name is Ramesh HG, working as Assistant Professor of Mathematics, Government First Aid College, Tiptur. Today I am going to discuss about second order linear partial differential equations. So, what is the meaning of second order linear partial differential equations? A partial differential equation which is linear with respect to dependent variables and its derivatives, and in which the coefficient or constants is called a linear partial differential with respect with the constant coefficients. A partial differential equation which is linear with respect to the dependent variables and its derivatives, and in which the coefficients or constants is called linear differential equation with constant coefficients. A second order linear partial differential equation is of the form a naught dou square z by dou x square plus a1 dou square z by dou x dou y plus a2 dou square z by dou y square plus b naught dou z by dou s plus b1 dou z by dou y plus c naught z is equal to f of x comma y, where a naught a1 a2 b naught b1 c naught are constants. Denote dou by dou x as d, dou by dou y as d dash, dou square by dou x dou y as d dash. Then the equation becomes a naught d square plus a1 d dash plus a2 d dash whole square plus b naught d plus b1 d dash plus c naught into z is equal to f of x y. Or f, this can be written as f of d comma d dash is equal into z is equal to f of x comma y. If the differential equation 1, all the derivatives that appear are of the same order, then it is called homogeneous differential equation. So, which is of most important, homogeneous differential equation with constant coefficients of second order. Thus, the equation a naught dou square z by dou x square plus a1 dou square z by dou x dou y plus a2 dou square z by dou y square is equal to f of xy, where a naught a1 and a2 are constants, is called homogeneous differential equations of second order. So, which is called as homogeneous linear differential equation of second order. In symbolical representation, a naught d square plus a1 d dash plus a2 d dash whole square into z is equal to f of x comma y, or f of d comma d dash into z is equal to f of x comma y. As in the case of ordinary differential equations with constant coefficients, the complete solution of linear differential equation consisting of two parts, namely CF and P, a complementary function and a particular integral. The complementary function of the equation 1 is the complete solution of the given equation f of d comma d dash into z is equal to 0, where the particular integral of the given function is a particular solution of f of d comma d dash into z is equal to f of xy. First, we shall see some rules of finding CF and Pi of the homogeneous differential equations. Second order homogeneous linear differential equation. A general homogeneous linear differential equation of second order is of the form a naught d square plus a1 d dash plus a2 d dash whole square into z is equal to f of x comma y. Or this can also be written as f of d comma d dash into z is equal to f of x comma y. So here, which is the second order homogeneous differential equation is of importance. So this equation can be written as a naught d square plus a1 d dash plus a2 d dash whole square into z is equal to f of x comma y, or f of d comma d dash is equal to a naught d square plus a1 d dash plus a2. To find the complementary function, put d is equal to m, which is very important. Put d is equal to, in place of d you substitute m, in place of d dash you substitute 1. Then we get the equation of the form a naught m square plus a1m plus a2 is equal to 0, which is called as auxiliary equation. So first you put the value of d as m and d dash as 1 in the given equation, and we obtain the equation of the form a naught m square plus a1m plus a2 is equal to 0. This is called auxiliary equation of the given equation. And solving the equation, we get two roots. solving the equation, we get roots. Case 1, the roots of the auxiliary equation are real and distinct, say m1 and m2. We write the CF as f1 of y plus m1x plus f2 of y plus m2x. So write the complementary function. It is very easy. f1 of y plus m1x plus f2 of y plus m2x. And if the auxiliary equation roots of the auxiliary equation are same, say m and m. In this case, the complementary function is given by f1 of y plus mx plus x into f2 of y plus mx. So this is the case. If roots are real and distinct, you write f1 of y plus m1x plus f2 of y plus m2x. If the roots are equal, you write CF as f1 of y plus mx plus x into f2 of y plus mx. Next, rule to find the particular integral, so which is of important. Particular pi is equal to 1 by f of d comma d dash into f of x comma y. Now we take the case 1. F of xy is equal to e to the power of ax plus b. Particular interval is 1 by f of d comma d dash into e power ax plus b is equal to 1 by f of a comma b e to the power of ax plus b. That is, substitute the value of d as a and d dash as b. So the case 1 is f of x comma y is equal to e to the power of ax plus b. Particular interval is 1 by f of d comma d dash into e power ax plus b is equal to 1 by f of a comma b. That means you substitute d is equal to a and d dash is equal to b in the particular interval, provided f of a comma b is not equal to 0. That is, put d is equal to a and d dash is equal to b in f of d comma d dash, provided f of a comma b is not equal to 0. Suppose if f of a comma b is equal to 0, then we write f of d comma d dash is equal to b into d minus a into d dash to the power of m into g of d comma d dash. Then pi is equal to 1 by g of b minus a comma b into x to the power of m divided by b to the power of m into m factorial by e to the power of ax plus b. For example, if m is equal to 1, then pi is equal to 1 by g of a comma b into x by b into e to the power of ax plus b. If m is equal to 2, then g of a comma b is equal to 1, then pi is equal to x square by 2b square into e to the power of x plus b. In this way, we can find the particular integral and complementary function in the particular integral. Case second. So when f of x comma y are trigonometric functions, x comma y are trigonometric functions, what to do is simply replace d square by minus a square, dd dash by minus ab, and this d dash whole square is equal to minus b square in f of d comma d dash, and proceed. If in this case the denominator becomes 0, apply the general method of finding pi as it is given in the case. When f of xy is equal to x to the power of m into y to the power of n, in this case f of d comma d dash y to the power of n minus 1 is ascending power of d or d dash, and operate on x to the power of m into y to the power of n term by term. So general method of finding pi when f of x comma y is any function of x and y. So pi is equal to 1 by f of d comma d dash f of x y. Resolve f of d comma d dash into partial fractions, and 1 by d minus m into d dash f of x comma y is equal to integral of f of x comma c minus mx dx, where c is replaced by y plus mx. Y is equal to mx plus c, y is equal to y plus mx after integration. So in this homogeneous linear differential equation, the following method is generally useful. If f of x comma y is of the form phi of ax plus b, then pi is equal to 1 by f of a comma b double integration of phi of b into dv, where b is equal to ax plus b. B must be replaced by ax plus b after integration. So in this way, we can solve the finding the CF and pi. First problem, we take first problem. So take the problem. Solve d square minus 2 dd dash plus d dash whole square into z is equal to e to the power of x plus 2y. So you observe that the given equation is homogeneous differential equation. So d square minus 2 dd dash plus d dash whole square into z is equal to e to the power of x plus 2y. Here you replace d by m and d dash by 1. D by m and d dash by 1. So auxiliary equation is m square minus 2m plus 1 into m square minus 2m plus 1 is equal to 0, or m minus 1 whole square is equal to 0. M is equal to 1 comma 1. You observe that the roots are repeated roots or equal roots. Therefore the complementary function is given by f1 of y plus mx, f1 of y plus mx. So y plus m is 1. So y plus x plus x into f2 of y plus mx, y plus x. So this is the complementary. This is a very simple problem. So we get the values of m as 1 comma 1 and they are equal. So complementary function is f1 of y plus mx plus x into f2 of y plus mx. So m is 1. So f1 of y plus x into f2 of y plus x. So you come to particular integral 1 by d square minus 2d into d dash plus d dash whole square into e to the power of x plus 2y. So replace a by d is equal to 1 and d dash is equal to 2. D is equal to 1 you substitute and d dash is equal to 2. So we get pi is equal to 1 by 1 minus 4 plus 4 into e to the power of x plus 2y, or cancel 4. So e to the power of x plus 2y. Therefore the complete solution is cf plus pi. So z is equal to f1 of y plus x plus x into f2 of y plus x plus e power x plus 2y. This is the solution of the given homogeneous partial differential equation. So once again the given equation is d square minus 2d dash plus d dash whole square into z is equal to e to the power of x plus 2y. So replace d by m and d dash by 1. So m square minus 2m plus 1 is equal to 0. M minus 1 whole square equal to 0. M is equal to 1 common. Therefore the roots are equal or repeated. So repeated root cf is equal to f1 of y plus x plus x into f2 of y plus x. Particular interval is 1 by d square minus 2d to d dash plus d dash whole square is equal to e to the power of x plus 2y. Replace d by 1 and d dash by 2. We get particular interval as 1 by 4 minus 4 plus 4 cancel e power x plus 2y. Thus the complete solution is z is equal to f1 of y plus x plus x into f2 of y plus x plus e to the power of x plus 2y. Take the second problem. 2r minus s minus 3t is equal to 5 into e to the power of x minus 5. So you observe that the value of r is dou square z by dou x square. Value of s is dou square z by dou x dou y. Value of t is dou square z by dou y square. Thus the given equation becomes 2d square minus dd dash minus 3d dash whole square. 2d square minus d into d dash minus 3d dash whole square into z is equal to 5 into e to the power of x minus 5. So the auxiliary equation is given by put d is equal to m and d dash is equal to 1. 2m square minus m minus 3 is equal to 0. This is the auxiliary equation. And solving m plus 1 into 2m minus 3 is equal to 0. M is equal to minus 1 comma 3 by 2. Here the roots are not equal, real and distinct. Therefore complementary function is f1 of y minus x into plus f2 of y plus 3 by 2x. This is the solution of this is the complementary function of the given problem. Or once again, here r is dou square z by dou x square, s is dou square z by dou x dou y, t is equal to dou square z by dou y square. Substituting we get to 2d square dd dash minus 3d dash whole square z is equal to 5 into e to the power of x minus 5. Auxiliary equation is given by 2m square minus m minus 3 is equal to 0, or m plus 1 into 2m minus 3 is equal to 0. M is equal to minus 1 comma 3 by 2. Cf is equal to f1 of y minus x plus f2 of y plus 3 by 2 x. To find the complementary function 1 by 2 d square minus dd dash minus 3 d dash whole square into 5 into e to the power of x minus 5. So you see that This is equal to, when d is equal to 1 and d is equal to d dash is equal to minus 1. You see, this can be factorized as d plus d dash into 2d minus 3d dash. Pi is equal to 5 into 1 by d plus d dash into 1 by 2d minus 3d dash into e to the power of x minus y. So you substitute for the second term, d is equal to 1 and d dash is equal to minus 1. 1 by 2 minus 3 into minus 1 into e power x minus y. So 5 we cancel, 1 by d plus d dash into e power x minus y. This is equal to x divided by x to the power of m. X divided by m to the power of 1. M to the power of 1, x to the power of 1 divided by x to the power of 1 divided by minus m to the power of 1. M is minus 1 into 1 factor into e to the power of x minus y. R is equal to minus x e to the power of x minus y. Since the denominator becomes 0, therefore they apply formula x to the power of 1 by m to the power of 1. So minus 1 to the power of 1 into 1 factor into e to the power of x minus y. Therefore the complete solution is given by z is equal to f1 of y minus x plus f2 of y plus 3 by 2x minus x into e power x minus y. So this is the complete. So z is equal to f1 of y minus x plus f2 of y plus 3 by 2x minus x into e power x minus y. This is the complete solution of the given homogeneous partial differential equation. Next problem is solve d minus d dash whole square into z is equal to e to the power of x plus 5. Solution. The auxiliary equation is m minus 1 whole square. So put d is equal to 1 and d dash is equal to m and d dash is equal to 1. So m minus 1 whole square is equal to 0, m is equal to 1 comma 1. Complementary function is f1 of y plus x into f2 of y plus x. Since the roots are equal, therefore you get f1 of y plus mx plus x into f of y plus mx. Pi is equal to 1 by d minus d dash whole square into e power x plus y. So d minus d dash is equal to 0 when d is equal to 1 and d dash is equal to 1. Therefore Pi is equal to x square by 1 square into 2 factorial by into e power x plus y, or x square by 2 into e power x plus y. Therefore complete solution is z is equal to f1 of y plus x into f2 of y plus x square by 2 into e power x plus 2y. This is the complete solution of the given differential equation. So in this way we find this complementary function particular integral and hence the complete solution of homogeneous partial differential equation. Okay, thank you.